In this lesson, we are going to remind ourselves of the basic principle behind the pressure altimeter, and to appreciate its limitations as a measure of vertical distance. We will also look at altimeter settings, and the reasons for using one rather than another. First, let's start with some basic definitions, so that we use the correct terminology. Altitude, when used on its own, without any qualifying prefix, such as density altitude or pressure altitude, means the vertical distance of a movable object above mean sea level. Sometimes it can be referred to as true altitude, in which case it means just the same thing as altitude on its own. Elevation uses the same datum as altitude, but the difference is that elevation is the vertical distance of a fixed object above mean sea level. By fixed object, we normally mean the ground. Therefore, elevation in this case is referring to the vertical distance of this runway above the sea. Elevations can be negative. Amsterdam Schiphol Airport, for instance, is 11 feet below mean sea level, and so has an elevation of -11. However, elevations do not have to refer to the ground. The top of this control tower has an elevation which will be the elevation of the ground on which it is built, plus the extra distance to the top. This leads on to the next definition, which is height. Height is the vertical distance of an object above a fixed datum. In this example, the aircraft has a height above the airport underneath it. Height is always less than altitude unless the elevation is negative. However, height can refer to either movable objects, such as aircraft, or fixed objects, such as this control tower. A tall obstruction, such as a TV mast, can be quoted both as a height above the ground on which it stands and an elevation above mean sea level. Where height refers to vertical distance of an aircraft, it does not have to be with reference to the ground. For instance, we might be interested in the aircraft's height above the top of a tower. Flight level is something different. Flight level is also known as pressure altitude. It is a pressure difference between that experienced by an aircraft and a datum pressure level of 1013 hectopascals. It is converted using the ISA-atmosphere relationship and expressed in feet. But it is a pressure relationship, and its true vertical distance will vary according to the temperature at the time. Under ISA conditions, that true vertical distance will be the same as the flight level or pressure altitude. Now let's consider the principle on which the altimeter works. We assume an ISA atmosphere with a pressure of 1013 hectopascals at mean sea level. If it is an ISA atmosphere, 10,000 feet will occur at a pressure of approximately 700 hectopascals. 20,000 will be at 450. And 30,000 feet will have a pressure of about 300 hectopascals. These numbers have been rounded slightly, but they are very close to the actual altitudes at which these pressures occur. But remember, these pressures will only be found at these levels on an ISA day. However, it would be very unusual to have a day which is exactly the same as the ISA atmosphere when you fly. This standard atmosphere is an average for all the regions in the world, from tropical to polar, and all the seasons of the year, hot or cold. Therefore, the altimeter is extremely unlikely to read your true altitude. This may be for one or two reasons. Firstly, even if the temperature distribution as you climbed were precisely as specified in ISA, the sea level pressure might not be 1013 hectopascals. Sea level pressure usually varies between about 950 and 1050 hectopascals, and is seldom the same from day to day. It often changes from hour to hour. So, if the sea level pressure were, say, 970, all the contour lines would move down together like this. And if it were higher than 1013, they would all move together upwards like this. We can solve this problem by altering the subscale setting of our altimeter, so that the instrument is reset to read 0 for the mean sea level pressure at the time. If the airport were at sea level and the sea level pressure were 995, this is what we must do. If we fail to do so, we have an error, which is given the name barometric error. Now suppose that we don't have this problem. Assume that the sea level pressure is 1013 on a particular day, but this time the temperature changes. Warm air will expand, and the effect is that the contour layers concertina outwards. Alternatively, on a cold day, the layers close together, and any given pressure level is found at a lower altitude. Therefore, if we wish our altimeter to indicate true altitude, we must make an allowance for the temperature difference from ISA. This error cannot be corrected on the instrument itself. We allow for it by using calculations or tables. If we fail to do so, we have an error, which is given the name temperature error. So we now need to decide what to set on our altimeter. Should we correct for barometric and temperature error? If we are near the ground and there is a danger of collision into terrain, the answer is obvious. Of course we should. Especially in fog and low cloud. The vertical distance of hills, mountains, ridges and tall structures is given as an elevation on our maps. We need to know our true altitude in order to ensure safe clearance. We must make sea level our datum by setting the subscale correctly. And if the temperature deviation from ISA is significant enough to make a difference, we must correct for temperature error. But what if we are high enough to be in no danger from terrain? In this case, it is more important to avoid colliding with other aircraft. We require vertical separation. This aircraft could be told to fly at 7,000 feet, whilst this one is told to fly at 8,000 feet. However, suppose that one aircraft has corrected for barometric and temperature error at a departure airport, where the sea level pressure and the temperature are lower than when they meet, and has not altered it since. His true altitude will be here. And suppose that this other one has corrected for barometric and temperature error at a departure airport, where the sea level pressure and the temperature are higher than when they meet, and has not altered it since. His true altitude will be here. There is a danger of collision unless both aircraft use the same datum pressure and deal with temperature error the same way. We have a procedure to deal with this. Once safely away from high ground, both aircraft set 1013 as a datum and do not make any correction for temperature. We call this flight levels. This aircraft is told to fly at flight level 70. This means 7,000 feet on 1013. This aircraft is told to fly at flight level 80. This is 8,000 feet on 1013. It may be that because of barometric and temperature error, this aircraft is really at 6,500 feet true altitude. But if so, this one will be at 7,500 feet true altitude. They are in the same part of the sky and are experiencing identical barometric and temperature errors. They will still have 1,000 feet vertical separation. Their true altitude doesn't matter, as long as there is no danger of either of them hitting the ground. Because of differing requirements at different stages of flight, there are three main altimeter settings in use. These are called QFE, QNH, and standard pressure setting, or sometimes simply 1013. These three-letter groups starting with Q come from a code used for Morse messages, Now that voice messages have replaced Morse in aviation, hardly any Q codes remain in common use, but some are still employed for pressure settings, radio bearings, and runway direction. QFE is defined as the atmospheric pressure at the aerodrome elevation. It is the subscale setting that will cause the altimeter to read 0 when the aircraft is on the ground. 0 datum is the airport elevation, not sea level. Effectively, this gives the pilot his height above touchdown. QNH is the subscale setting that will cause the altimeter to read the airport elevation when the aircraft is at touchdown. Broadly, it gives a pilot his altitude above mean sea level, but this is not the correct definition because of the possibility of temperature errors. The definition to be used is always the one we have just given. Look at it now and remember it. QNH is the subscale setting that will cause the altimeter to read the airport elevation when the aircraft is at touchdown. Standard pressure setting, or 1013, is what we set when required to fly flight levels. Flight levels are always given in hundreds of feet, and usually only 500s and whole thousands of feet are used. Thus, 17,500 feet becomes flight level 175. This is a shorthand way for the air traffic controller to say, fly at 17,500 feet on a pressure setting of 1013 hectopascals. It takes less time on the radio. QFE is used for most PPL training. It is easy to understand, and it looks normal to most beginners to see 0 on the altimeter when you are on the runway. Circuits vary from airfield to airfield, but typically students are taught to start the crosswind turn at 500 feet, fly the downwind leg at 1,000 feet, lose some height in the turn to begin the base leg at 800 feet, and start the final turn at 600 feet. If the airfield elevation is, say, 270 feet, it is easier to remember these numbers than the QNH equivalent of 770, 1270, 1070, and 870. Furthermore, if you then go to another airfield where the elevation is, say, 450, it is easier to apply your standard circuit heights than work out new altitudes for each part of the circuit. However, when you depart the circuit, QFE is meaningless. You must set QNH in order to relate your altimeter to elevations, especially if there are obstructions or high ground in the vicinity. QNH is used by airline pilots. Airline pilots do not always use the same airfield, and therefore expect to have to familiarize themselves on each flight with the altitudes to be flown on the approach. This is normally done just before top of descent. At a quiet moment, a few minutes before the letdown is expected, the pilots hold a short intercom briefing, when they look at the approach chart and agree the procedures that they will use. This is a typical approach chart. This one is for the ILS to runway 08 left. At Munich. Note that the touchdown elevation of 08 left is 1,467 feet. This is a plan view of the approach. Here is the runway. Note that the final approach starts at 12 nautical miles DME range from the Delta Mike November. DME means distance measuring equipment. It gives the pilot a range from a ground beacon. Note that we pass over the locator, also known as the Munich Mike November Echo, at 4.7 nautical miles DME range from the Delta Mike November. We also pass over a facility called the middle marker. Note also that if we have to go around, our missed approach procedure takes us over an obstruction of elevation 2,133 feet, and that there are also several other tall obstructions in the local area. Now let's look at the final part of the approach in profile. Here is the final approach fix at 12 miles DME. The required altitude is shown as 5,000 feet QNH, or you could fly a height of 3,533 on QFE. The difference is the elevation of 1,467. As you pass the locator at 4.7 miles DME, you should be at 2,680 feet QNH, or 1,213 feet QFE. When we get to the middle marker, we should be 0.6 of a mile from the runway. This is the warning that we are very close to our decision point, which can either be given as a decision altitude or as a decision height. If at the decision altitude we can't see the runway, or at least 2 bars of crossbar lighting because of low cloud or fog, we have to go around and follow the missed approach procedure. If you remember, it took us over a high obstruction, which we won't be able to see if we are in cloud or fog. We must be on QNH to know that we are clear of it. As part of the go-around procedure, we will carry out the after-takeoff checks. These include setting climb power, raising the gear, setting the flaps as required, and several others to get the aircraft into a cruise rather than a landing configuration. They are vital to safe flight. If we had flown the approach on QFE, we would also have to ensure that the after-takeoff checks included a reminder to set QNH. This is a distraction that we can do without when we are already busy. Therefore, airline pilots usually use QNH. It makes little difference to them whether they set QFE or QNH on the approach, because they're going to have to brief themselves on the check altitudes anyway. But it means that there is one less thing to do if they have to go around. At Oxford, we teach QNH from the very first flight, because we are preparing students for the airlines. Let's summarize this lesson. We said that we were going to remind ourselves of the basic principle behind the pressure altimeter, and to appreciate its limitations as a measure of vertical distance. We would also look at altimeter settings and the reasons for using one rather than another. We defined altitude, elevation, height, and flight level or pressure altitude. We said that ISA was only a datum atmosphere for calibration purposes, and was unlikely to be encountered on any actual day. On a real day, the sea level pressure may not be 1013. In this case, we have a barometric error, and the temperature distribution may not be according to ISA, in which case we have a temperature error. We therefore have to set our altimeter to a known datum pressure, and, if necessary, correct for temperature error. However, if we are high enough to be clear of obstructions, we are not interested in our true altitude. It is more important to have vertical separation from other aircraft. We therefore set 1013 and fly flight levels. At an airport we can use QFE. This is easier for beginners. QFE is the subscale setting that will cause the altimeter to read 0 when the aircraft is on the ground. The 0 datum is the airport elevation, not sea level. We can also use QNH. This is generally used by airline pilots. QNH is the subscale setting that will cause the altimeter to read the airport elevation when the aircraft is at touchdown. It is also usually very close to altitude above mean sea level, but this is not the correct definition because of the possibility of temperature errors. When we depart the airfield, we must be on QNH in order to have a datum that relates to the elevations of vertical obstructions. This completes this lesson. We shall go on to consider the procedures for changing our altimeter settings in the next lesson.